Okay, let's just dive right in. Today we're going deep on a piece of technology that really underpins so much of modern AI. We're talking about Google's Tensor processing units,
Yeah.
TPUs.
Right.
And for you, the listener, this isn't just a story about, a faster chip. It's really a masterclass in how a company's internal needs can spark this huge vertical innovation.
It's the classic story. They needed something the market just couldn't give them, so they built it themselves. And, well, it changed everything.
So what's our mission for this deep dive? Where are we taking the listener?
Our mission is to trace that exact history. We're going to go from this moment of crisis, the single napkin sketch idea back in 2013, all the way to what they are today.
Which are these massive interconnected machine learning supercomputers.
Exactly. We need to figure out how you get from A to B, from a single bottleneck to a global system.
And when we say massive, we should probably set the stage right away. I mean, the sources mention the latest, the 7th generation, Gen 7.
Yeah, and these are configured into these enormous pods. We're talking 916 chips in a single pod.
9,000 chips.
9,000 all working together, and they're engineered for just incredible performance, especially with these new dense, low-precision number formats like FP4.
Okay, let's unpack this. Where did the necessity for this specialized hardware even come from? Because it wasn't about selling chips at first.
Not at all.
This was purely an internal survival thing, right?
Yeah.
Centered around inference.
The necessity was absolute. I mean, it hit them like a freight train. The year was 2013.
Right.
And deep learning models, especially for things like speech recognition, were getting way, way better. The more data you fed them, the better they got. It was obvious this was the future.
But the cost of running them.
It was spiraling, completely out of control. The breaking point was an improved speech model they wanted to roll out, something that would be a huge improvement for millions of users.
This is the part of the story that I find just so compelling. It all came down to a terrifying back-of-the-envelope calculation.
Yes.
What did that piece of paper actually say?
It was startlingly simple and horrifying. The calculation was basically this. If they wanted to roll out that new speech model to, say, 100 million users for just a few minutes a day,
Okay.
they would need to double the total number of computers Google owned overall.
Not just in one data center.
No.
The entire global infrastructure.
The entire thing. Double it. Just to run one improved service?
Wow. That's not an optimization problem anymore. That's an existential crisis. You just can't do that.
You can't. And that realization, that was the moment the TPU was born. The answer wasn't more CPUs. It was specialized hardware, custom built for one thing.
Dense, low-precision linear algebra.
Exactly. The core math of neural networks. CPUs are generalists. They weren't built for this kind of repetitive, intense work.
So the idea hits in 2013. Development starts. And then the first chip, TPU v1, is in their data centers by 2015. That is an incredibly fast turnaround for custom silicon.
It tells you how urgent the problem was, and the performance metrics, I mean, they just proved it was the right call. It was a massive, immediate leap.
Give us those numbers. What did that first breakthrough actually look like?
Okay, so in terms of energy efficiency, TPU v1 was 30 to 70 times more efficient than the CPUs or GPUs they were using at the time.
30 to 70, that's a generational leap, not an incremental one.
Oh, absolutely. And for pure speed, just raw throughput, it was 15 to 30 times faster.
So you solved the power crisis and the compute crisis in one go. But how? How did they do it?
By being ruthless. They specialized. They threw out all the complex stuff a CPU needs, caching, branch prediction, all of that, and devoted almost the entire chip to one thing.
A massive matrix multiply unit, the MMU.
Right, the engine for all that linear algebra. By just streaming data directly through that dedicated engine, they cut out all the overhead that slows a CPU down.
What's really fascinating to me is that this first generation was developed before the transformer architecture, before all of that.
A crucial point. The initial focus was all on speech recognition and vision models, convolutional models.
But they had to be thinking ahead, right?
Yeah, they did. And there's a great little detail from the design phase. They actually squeezed a last-minute change into TPU v1 to add support for LSTMs.
Which were the hot thing for language modeling back then.
Exactly. And that little pivot, that one change, it let them immediately start running language translation tasks. It was this incredible piece of foresight that, language models were going to be a huge demanding workload.
So as the program matured, the focus shifts. It's not just about inference anymore. It's about training these huge models, and the scale just explodes.
Right. We go from that single PCI card, the TPU v1, to what we have now. true machine learning supercomputers.
And this is where the strategy gets really deep. It's all about this co-design philosophy, right?
Yeah.
Hardware and software evolving together.
They have to. You can't build them in a vacuum. But the core challenge is insane.
The crystal ball problem.
Yes. The hardware designers have to forecast where ML research is going to be 2.5 to 6 years from now.
That seems impossible. The field moves, like, weekly. How do you build a chip today for a model that doesn't even exist yet?
It's incredibly difficult. If you bet on the wrong model, you've just wasted billions of dollars and years of work.
So how do you manage that risk?
They use what you could call an insurance policy strategy.
Okay.
They integrate certain features or capabilities into the hardware, even if the research supporting them is still just theoretical. Maybe it's a new way to access memory or an experimental math operation. They'll devote a small, measured area of the chip to it.
So if that research trend bears out, as they say,
If it becomes the next big thing, they're ready. They have hardware support on day one.
and if it doesn't,
They've only lost a tiny fraction of the chip's real estate. It's a much safer bet than going all in on one big, uncertain idea. It's how they stay ahead.
which brings us back to the current scale.
Hmm.
These Gen 7 pods with 900 and 216 chips, that's not just a pile of hardware. It has to be a single, cohesive machine.
The engineering challenge is staggering. You have power, you have cooling, and most importantly, you have interconnectivity. The chips have to talk to each other at unbelievable speeds.
And they use these custom high-bandwidth interconnects, right? Like optical fibers laid out in these complex torus patterns.
Exactly. Latency is the enemy of large-scale training, and that's why they also lean so heavily on low-precision formats.
Let's touch on that. FP4, 4-bit floating point. That saves a ton of memory and boosts speed. But doesn't it hurt the model's accuracy?
It's a trade-off, for sure. And you can't just flip a switch to FP4 and hope for the best. It required huge software innovations in parallel new algorithms and calibration techniques to train the models reliably with those constrained numbers without losing quality.
That's the perfect transition, the software stack. Because all this amazing hardware is basically a paperweight without the software to manage it.
Completely. And that's where the external access comes in with the cloud TPU program.
Right, so you can rent this power. But making 9,000 chips feel like one machine, that's a software problem.
It is. You can't manually schedule that. It's why the layers they built are so critical, specifically the internal system called pathways.
And most researchers interact with that through JAX, right? That's the main entry
JAX, a
point.
well-worn path, yeah. But Pathways is the magic underneath. What Pathways does is provide the illusion of a single system image.
The illusion of one giant computer.
Precisely. A researcher writes their code as if they're talking to one machine. Pathways handles everything else, partitioning the data, managing communication, handling it if a chip fails. It can give a single Python process access to 20,000 devices and make it all just disappear.
And the bridge between the code and the silicon is the compiler, XLA.
Right. XLA takes the abstract model from JAX and maps it perfectly onto the specialized TPU hardware. It's the translator that unlocks all that performance.
The sources say this whole system enables what they call geoscale training, like for Gemini.
Yeah, the scale is just mind-boggling. Inside a pod, you have those custom high-speed interconnects.
Okay.
Between pods in the same building, you use the data center network. But for the biggest jobs, Pathways will coordinate across long-distance links between multiple cities.
So a single training job, driven by one Python process, is running across continents.
Yes. Seamlessly.
You know, it's a good reminder that all this innovation stands on the shoulders of so much other work. I mean, Google itself was built on academic research, TCP/IP, RISC processors, PageRank.
And deep learning itself, as you said, came from ideas that were around for 30 or 40 years. Neural networks, backpropagation. The TPU is what happens when you apply that long-term research to a massive modern-day crisis.
Which brings us back to that 2013 napkin sketch. The focus now in hardware design, it seems, isn't just about making the next TPU a little bit faster. It's about finding completely new ways to be more efficient.
That's the whole game now. The key driver for future hardware isn't just raw speed, it's performance per watt.
The energy problem.
It's a huge problem. These large models consume gargantuan amounts of power. The next great challenge is creating systems that are way, way lower energy while keeping all that quality and speed.
So what does this all mean? We've gone from this internal crisis in 2013, a problem that threatened to double their entire infrastructure,
To this specialized hardware that delivered a 30 to 70 times efficiency gain.
which then evolved into these global, multi-city supercomputers,
Yeah.
all managed by this incredibly sophisticated software like pathways.
And the whole thing depended on their ability to look into that crystal ball, to forecast the technology needs to 3, 5 years out.
That co-design philosophy is it's a powerful engine, but it takes so much insight and a huge tolerance for risk.
It's what separates a true vertical innovator from just a component supplier.
Right. So if hardware designers have to correctly predict ML research trends 2.5 to 6 years ahead to build an effective chip, here's a parallel challenge for you to think about. We know this deep learning revolution was built on academic ideas from 30, 40 years ago.
The early neural net papers.
Exactly. So what foundational academic research being explored today? Maybe it's something totally different, like spiking neural networks or analog computing or some new physical material for computation. What is the equivalent of that early research now that will define the next generation of computing and society a decade from today?
That's the question. The TPU story shows that the biggest breakthroughs often come from betting on that quiet, fundamental research long before it becomes an undeniable trend. Thanks for diving deep with us.
See you next time.